Welcome back to the deep dive. You know, when we talk about hunting for life beyond Earth, our thoughts, well, they usually jump to the familiar places, right?
Absolutely. The ones that feel sort of Earth-like.
Exactly. We think icy moons, maybe Europa, Enceladus.
Titan with its methane lakes or, good old Mars.
Yeah, they make intuitive sense. There's water or conditions we can kind of wrap our heads around as being potentially habitable.
Hmm.
But today's deep dive, well, it asks us to completely ditch that Earth-centric thinking. We know life here can survive some truly insane conditions. Think deep-sea vents, boiling temperatures.
Life finds a way, as they say, even in extreme heat.
Right. So today we're taking this, let's call it a calculated leap, out to the solar system's edge. To Neptune, that big blue ice giant that looks totally hostile.
This is the last place you'd look?
Exactly. Our mission, exploring the, frankly, radical idea of life deep inside Neptune.
It does sound like pure science fiction, I have to admit. But if we can just step back from insisting life needs sunlight and oxygen, then maybe, just maybe, the basic chemical building blocks could be there.
So that's the core hypothesis we're digging into.
Pretty much. It argues that, a completely non-Earth-like life form might be possible on Neptune. Why? Because it has boiling hot water, ammonia, and methane deep down.
Okay.
And the idea is that these things, under immense pressure, could actually give life a tiny chance to arise, some kind of specialized biological activity.
Okay, so our goal for this session is clear. We need to really unpack the arguments suggesting life could somehow overcome Neptune's, well, frankly, punishing physics and chemistry.
Right, the extreme cold, the winds, the pressure.
We're not looking for little green men, obviously. We're looking for whether the chemistry itself allows for any kind of living system under those specific conditions.
Precisely. We need to think of the planet less like an obstacle course and more like a unique kind of chemical engine.
All right, let's start with those environmental challenges. The source material describes Neptune in ways that sound purpose-built to destroy life as we know it.
It's definitely not welcoming.
We're talking about these deep oceans that are incredibly hot, right?
Incredibly
hot. Yeah, under immense pressure.
Winds faster than the speed of sound.
Supersonic speeds, yes.
And this mind-bending idea of diamond rain, where carbon gets crushed into actual diamonds and falls.
It paints a pretty harsh picture, doesn't it? And that environment is absolutely lethal for Earth-based biochemistry, no question.
So where's the first major hurdle for any potential life?
The atmosphere. Straight up. It's mostly hydrogen and helium.
Unlike ours, which is nitrogen and oxygen.
Exactly. Earth life runs on oxygen, fundamentally. Nitrogen is crucial too. So any hypothetical Neptunian life would need a completely different metabolic setup. It would have to evolve to take in what's abundant there.
Meaning hydrogen and helium.
Especially hydrogen. It would need a form of respiration based on hydrogen. Okay, so breathing hydrogen, what would exhale? Not carbon dioxide like us.
The theory suggests methane, CH44.
Methane. Wait, okay, let me play skeptic for our listeners here. Methane is carbon plus hydrogen. If it's inhaling just hydrogen, 2H22 from the atmosphere, where's the carbon C coming from to make the methane?
Yes. Good question. Crucial point. It can't just grab carbon from the upper atmosphere easily. The carbon has to come from the environment around it. From the ocean itself.
The boiling ammonia water ocean.
Exactly. That deep layer, that sort of supercritical slush, contains dissolved carbon compounds. So imagine this hypothetical life form pulling in hydrogen from the atmosphere.
Okay.
Combining it with carbon it gets from the ammonia water ocean around it,
Uh-huh.
and then releasing methane, CH44 as waste, back into the water and eventually the atmosphere.
A completely different chemical cycle.
It's a closed loop, essentially flipping our familiar carbon-oxygen cycle into a hydrogen-methane cycle.
Wow. Okay, that reframes harshness, less as pure destruction and more as specialized chemistry.
It's about adaptation to available resources.
But chemistry is only half of it. What about the physics? You mentioned pressure earlier. We keep having to remind ourselves life doesn't need our comfort zone.
And the pressure on Neptune is, well, astronomical.
Mm.
It's a very serious challenge. See, the water deep inside Neptune isn't liquid water like we swim in.
Right, you mentioned boiling hot.
Under that thick atmosphere, the combination of extreme pressure and intense heat creates something called a supercritical fluid.
Supercritical. Okay, what does that mean practically?
It's a fascinating state of matter.
Yeah.
It acts like both a gas and a liquid simultaneously.
Oh. Yeah.
Well, it can diffuse through things like a gas, but it can also dissolve substances like a liquid.
Which would be perfect for complex chemistry.
Exactly. Perfect for the kind of radical chemistry we're talking about, mixing hydrogen and dissolved carbon.
But hold on. Surviving that kind of pressure, we talk about deep-sea creatures on Earth in the Marianas Trench, and that's incredible pressure.
It is.
But how do we even begin to justify life surviving in a supercritical, high-pressure, ammonia-laced fluid? That seems like a whole other level of evolutionary leap.
We justify it by looking at the principle of adaptation itself. It's the core of evolution. If life here could evolve mechanisms to withstand the crushing depths of our oceans,
Okay.
then it's reasonable to hypothesize that any life originating on Neptune would simply have evolved over eons to be perfectly optimized for those specific physical conditions.
So the pressure isn't necessarily a barrier, it's just the environment it grew up in.
Precisely. Pressure doesn't halt chemistry. It just changes the rules of the game. It selects for organisms with structures strong enough or maybe fluid enough to handle it.
All right, that deals with pressure. But that brings us to the other huge physics problem, energy. On Earth, pretty much all life depends on the sun, right? Directly or indirectly.
The base of most food chains, yes.
Yeah.
Photosynthesis.
But sunlight definitely isn't reaching down into Neptune's deep, dark, supercritical oceans.
No chance. It's far too deep and the atmosphere's too thick.
So, doesn't that kill the theory right there? No sun, no energy, no life.
Not necessarily. Not if we consider other energy sources. Sources that we know exist.
Like what? Geothermal?
Sort of, but on a planetary scale. We often define the habitable zone based on distance from a star for liquid water. But Neptunian life, if it exists, might completely bypass the need for stellar energy. It could use internal energy.
To planet's own heat.
Exactly. Neptune, being a giant planet, has a hot active core. That internal heat radiating outwards provides a stable, incredibly long-lasting energy source. It could be enough to drive the chemical reactions needed for life.
So the planet's core basically acts like the sun for these potential organisms.
In a functional sense, yes. It's the primary power source. That's a massive paradigm shift for how we search for life, isn't it?
It really is. But wait, if this life depends entirely on core heat and lives way down in these super pressurized, supercritical oceans, wouldn't that make it practically impossible for us to ever find or confirm? It'd be locked away in the deepest, hottest layers.
That is the major challenge for verification. Absolutely. It makes direct detection incredibly difficult with current technology, maybe impossible.
So it might be there, but we could never know.
Well, the analysis we're drawing from suggests life might not only be in the absolute deepest layers, there could be other ways to get power a bit closer to, well, up.
Okay.
Two possibilities are mentioned. One is utilizing charged particles, ions, caught in Neptune's powerful magnetosphere.
Energy from space, but not sunlight.
Right. The other is more like traditional geothermal activity chemical energy released, where the core's heat interacts intensely with the materials in the layers above.
So it's not necessarily confined just to the deepest abyss.
It could potentially exist in multiple layers where conditions and energy sources overlap favorably, which makes the possibility, well, slightly less remote, maybe.
Okay, let's follow that chemical trail again. You mentioned methane earlier. Let's connect Neptune's most famous feature, its beautiful blue color, back to this life hypothesis. That blue is caused by methane in its atmosphere, right?
Correct. Methane gas absorbs red light and reflects blue light.
And the proposed metabolism for this life involves taking in hydrogen and producing methane?
Yes.
So suddenly that blue color isn't just geology. It could be a biological signature. A hint.
It's suggestive, perhaps. But the real significance of the methane, according to this hypothesis, isn't just that it's there. It's about where it is and how much.
Meaning?
Well, if the methane was just formed non-biologically, abiogenically, you might expect it to be concentrated in specific layers, dictated purely by temperature and pressure. Chemical equilibrium.
Okay. Makes sense.
But the observations and the models based on them show high concentrations of methane both dissolved in those deep supercritical oceans and significantly present up in the atmosphere.
And why is that particular distribution pattern so important? Why is that the hint?
Because imagine billions upon billions of microscopic organisms living in that ocean layer.
Okay. Like a vast plankton bloom, but hydrogen-based.
Sort of, yeah. And they're all constantly exhaling methane as waste. That continuous large-scale release of methane from the ocean bubbling up or diffusing up into the atmosphere. That's exactly the kind of signature you might expect from a widespread dynamic biological process.
Rather than just static chemical layers.
Exactly. It suggests something is actively producing and releasing it from the ocean depths into the atmosphere over time. Life is proposed as that something.
Okay, so if this process is real, what kind of life are we actually talking about? We mentioned microbes. We're definitely not picturing like complex swimming creatures, are we? Hydrogen-breathing whales.
Yeah, probably not whales, no. Given the extreme conditions, the intense pressures, the heat, the dynamic fluids, evolution would likely favor small size and rapid reproduction.
So microscopic.
Almost certainly, yes. Think vast populations of unicellular organisms, like, as you said, the Neptunian equivalent of Earth's deep ocean microbes or plankton, just running on a completely different chemical engine.
Any chance of anything more complex?
The sources suggest that maybe small multicellular structures aren't entirely impossible, perhaps simple filaments or microbial mats, but primarily you should picture vast, essentially invisible colonies thriving under crushing pressure and intense heat.
Wow. This whole deep dive, it really has flipped the script on how we view extreme environments. We started with Neptune feeling like this hostile, destructive place,
Right.
defined by diamond rain and boiling oceans.
Completely unwelcoming from our perspective.
But looking through this lens of extreme, specialized adaptation,
Right.
we've actually built a case, or at least explored a case, for a planet that might provide all the necessities for a unique form of life.
Internal energy, the right chemical fuel like hydrogen, the basic ingredients like carbon and water, even if it's supercritical water.
It all hinges on life being able to totally abandon the rulebook we're used to on Earth. Shedding the need for sunlight, for oxygen, for moderate temperatures and pressures.
And that radical shedding of our earthbound assumptions, that's really the big takeaway here, isn't it?
Yeah.
If life's chemistry can actually work by breathing hydrogen, using ammonia and methane, powering itself from a planet's core instead of a star, it forces a critical reevaluation of everything. Our definitions of life, of habitable zones.
So what does this mean for you listening to this? It means you now understand that the search for life isn't, and maybe shouldn't be, confined just to planets that look like Earth, those pale blue dots near yellow suns. It really opens up the possibility that the cosmos could be filled with an absolutely staggering range of life chemistries, things we haven't even conceived of, let alone started searching for.
And that leads to the final thought we should leave you with. We have to ask the question, if life really can thrive on a world like Neptune, fueled by its own core, living in supercritical oceans, what does that tell us about the fundamental rules of biology we thought were universal?
Have we been applying Earth's rules too narrowly to the rest of the universe? Exactly. What does this imply about the sheer range of chemical possibilities for life? How many other impossible environments might actually be teeming with life, just waiting for us to broaden our perspective?
An incredible, almost humbling thought to chew on. It proves that sometimes the most fascinating possibilities for life hide in the places you'd least expect. You are now thoroughly informed on the truly radical, blue sky thinking about life in the solar system's deep freeze.